Hello, this video is on one of these sort of epic mechanics questions that they like to throw in, particularly in dynamics questions. So let's see how we get on with this. Usual thing, look at the diagram first, then read through the text to see if there's anything that's not on the diagram already. So we've got a block of mass 3m, right, we can add that on. So that's 3m, placed on a horizontal surface at point A, light inextensible string, touch the block passing over the peg. String is horizontal, yeah, great. Particle of mass 2m attached to the other end of the string. Released from rest with a string taut and the string between the peg and the particle vertical. Right, okay, so it's just the masses that I can put on, and all the rest of it is just essentially describing the geometry of the situation, that all these things are moving in the same plane. We could draw a vertical plane through all of this, and it restricts our dimensions of motion. Assume no air resistance. Yeah, well, we always do that. Size of the block is negligible. Yeah, pretty standard. Horizontal surface is smooth between A and B, rough between B and C. Right, so between B and C, we've got a coefficient of friction of 0.8 in here, 0.8. By forming equations of motion for both the block and the particle, find the acceleration of the block between A and B. Right, so let's add on a few little bits. It's quite a small picture here because the question's so big. So we'll put on our T's. For those, we've got an mg, so that's 2mg going down there. So 2mg. Yeah, the other one, well, whatever, let's mark it on anyway. So we've got 3mg. And then we've got our reaction force, which we can come back to, just don't really have enough space on the diagram. Right, mark on acceleration. So acceleration, it's not going to suddenly be magically pulling this hanging mass upwards. So let's draw the acceleration down. Not that it would really matter anyway, we'd still get the right answer. So we're doing F equals ma for each Newton's second law for each of the particles. So we're going to have that T is equal to 3ma and that 2mg minus T is equal to 2ma. So we can just add these together, which will eliminate the T's. So we're going to have 2mg is equal to 5ma, 2mg equals 5ma. So that's 1, that's 2, this is 1 plus 2, gives us that. Cancel the m's, and then we've got our acceleration is 2 over 5g. So 2/5 of g is our acceleration. What have they called the acceleration? Have they written units anywhere on there? They haven't. So put the units on. Right, so that's part 1 done. Given that the distance between the points A and B is 1.2 meters, find the speed of the block when it reaches B. So we just got this force T applied onto there. I mean, we could just do a straight SUVAT on this because we've got a constant force between A and B. So you might be thinking at this point, well, I'm happy with using v squared equals u squared plus 2as. Of course, you could be thinking that the change in the velocity, so putting this in quotes as well, so half mv squared minus half mu squared, so I put it in quotes because of course we've got 3m as the mass here, not m, is going to be equal to the force multiplied by the distance, and the force is the mass times the acceleration, and then the distance is s. So this just drops out once you cancel the m's. That's produced our v squared equals u squared plus 2as. So that's what we're going to be using. U is 0, so we've just got that v squared is equal to 2 times a times s. So that is, what did they say the distance was? 1.2 meters. So 6 over 5 multiplied by 2a, which is 4 over 5 g. So v is going to be equal to the square root of 24g over 25. So no problem with that one. By forming equations of motion for both the block and the particle, find the acceleration of the block between B and C, right? So we're just repeating part one here, but we're chucking in friction as well. So let's just section off a little bit. I'm hoping I'm going to squeeze all these in. We've now got that T minus the friction, so that's minus mu R. So mu is 4 over 5 and R is 3 mg. So that is for the block, that's going to be equal to 3m times the new acceleration. And then we've still got 2mg minus t is equal to 2ma on the other one. So again, we're adding these together in the same way as we did before. Add these together, which means we're going to get the 5ma again on the right hand side. The t's are going to cancel, but this time we've got 2mg minus 12 over 5 mg, so that is going to be minus 2 over 5 mg. So the friction is slowing down the motion here. We can cancel the masses and we're going to get the acceleration is minus 2g over 25 meters per second squared. So again, remember to write the units in. I've just run out of space on the screen. So that's given us the acceleration between B and C. Now we find the speed of the block when it reaches C. So we're doing exactly the same thing again that we had before. So we've got that v squared equals u squared is now this old v, so 24g over 25 minus 2as. So the 2a is minus because we've got a negative acceleration, so 4g over 25 is our 2a, and s, what was it, 0.9 multiplied by 9 over 10. Wow, so we've got 240 minus 36, so 204 over 250 g square rooted, so 102 over 125. I mean, you can simplify that down. I mean, it doesn't really matter. You stick it into the calculator if you really need to. Oh, I've now already square rooted it. So I should really have left that square root off because I've still got v squared on the left-hand side, and then say that v is equal to the square root of 102 over 125. I'm not really going to think about, hasn't got any obvious factors, and I don't really care if that can be particularly simplified. We can just stick it into the calculator if you want to know what an approximate number is going to be for that. Explain why it is important to assume that the size of the block is negligible. Right, so whenever they're talking about these sort of things, you want to go into, well, what's happening with the block? They've already told us there's no air resistance acting. I mean, I know they've made that an assumption, but it feels as though they don't want us to go down that route. So what's happening with the block? It's moving from A to B on a smooth surface, then it's transitioning at B onto a rough surface. So if this block has got volume, then you're going to get a transition going on there where the block is going to be partly on the rough surface and partly on the smooth surface. So we could say something like if the block has volume, then it's always nice to do an if-then structure. Then at B, it will be partly on the smooth surface. Probably going to run out of space here, but you can see where this is going, and partly on rough surface, and partly on the rough surface. So yeah, just be writing that bit out. So there's a lot. It looks as though there's a lot going on because you've got the usual thing that happens in these mechanics questions where they draw a picture and then state all of these assumptions that they are necessary, but they cloud the question just from a straight solving the problem point of view. You think they could have left out so much of this text. But you do need to be aware. I mean, it is still highlighting an important point that you need to be aware of all these assumptions, that you do have a light inextensible string so that you can do all of this F equals ma. You know, you haven't got the extra mass in the string. You haven't got the change in the acceleration because the string is stretching, that you've got a smooth peg. You know, that this peg is just changing the direction of the forces, but is still keeping this closed system of block and mass and string. That the string is horizontal, so we can treat this force moving in one horizontal plane across the table of what the block is experiencing, that it's hanging vertically on the other side of the peg. So again, we're in that same plane. We've got this motion in one dimension and then combined for the two objects in a single plane. All of these assumptions are really important. The assumption of no air resistance. We can't solve the problem by putting all of these things in anywhere near as easily. So we do have to keep stating that we're making these assumptions, but it clutters up the question. So you're caught then between these two stools of, well, I don't really care about this for solving the exam question, but I do care about it for doing proper science. So don't think you can just ignore all of this stuff. You can ignore it for answering the question because you know what's going to happen in an exam question, but don't ignore it from a science point of view because they really, really are important. And otherwise, we're going through the same stuff. We're doing Newton's second law over and over again with a little bit of Suvat, and we're reminding ourselves of where some of the Suvat equations come from. In this case, the conservation of energy version, the v squared equals u squared plus 2as. So yeah, nice question all in all.